In this lesson, we will discuss the basics of solutions, how to identify a type of solution, solubility, and solubility curves. As you know from previous courses, a solution is a homogeneous mixture of two or more substances. When you have a solution, you have a solute that is present in a smaller quantity that is dissolved in the solvent, which is the substance present in a larger amount. The solvent is the substance that is doing the dissolving. There are lots of different examples of solutions, and what's important to remember is that not all solutions are similar to a saltwater solution where you have a solid dissolved into a liquid. Vodka, for example, is a liquid dissolved in another liquid where we have ethanol dissolved in water, which is similar to vinegar, where we have acetic acid, which is a liquid, dissolved into water. Brass is an example of a solution that's made by dissolving one solid in another. In brass, the solvent is copper, and it's identified as the solvent because it's in all types of brass, it's present in a larger amount. There are many different kinds of brass that have different properties that will have different ratios of copper to zinc. But in all cases, the zinc is the solute, and it's dissolved into the copper. Now, it might be difficult to imagine how you would make a solution that's made of two solids, because you can't really just jam the two solids together. But the way that a solution of solids is made, like brass, is to melt the solids into their liquid state and then allow them to cool and return to solid. And when they're solid, they're a solution because when you look at a sample of brass, for example, it only looks like one substance. Air is an example of a mixture of gases. In the air that we breathe, nitrogen is identified as the solvent because it's the one that's in the largest quantity. Air is 4/5 nitrogen, and other components are the solutes, which are oxygen, which is the majority of the remainder, and then there are other gases in small quantities such as argon and methane, CH4. Soft drink is an example of a solution that is made by dissolving sugar, which is a solid, and a gas, carbon dioxide, in water. Now, when you have a solution, it can be identified as being an electrolyte or a non-electrolyte. And we've seen this before in our studies of properties of substances. We talked about how ionic compounds, when they're dissolved in water, they will conduct electricity. The term that we use to describe this type of property is that the substance is an electrolyte. So ionic compounds, and as you'll see later, acids and bases, which are really considered similar to ionic compounds, are electrolytes. Non-electrolytes will not conduct electricity when they're dissolved in water. So something like sugar, which is a molecular compound, when it's dissolved in water, it will not conduct electricity. And we need to use conductivity apparatus, like we did earlier in the year, in order to determine if something is an electrolyte or not. Another important item to recall is what's actually happening when we dissolve something. And when you dissolve something in water, we're actually hydrating the particles. And when we say hydrating, what we mean is that the water is actually surrounding the solute particles. So in an ionic compound, you'll recall that the positive and negative ions are separated into solution, and the water molecules will surround the cations and the anions. And you'll notice that the water molecule is pointing in different directions in each of these examples. Water, being a polar molecule, has a slightly negative end where the oxygen is. And so with the cation, the water molecules are all turned with the oxygen facing the cation. With the anion, the hydrogen in the water is more attracted, and therefore the water is pointing in that direction at the anion. Now, if we want to talk about solutions in a quantitative way, we can talk about what is referred to as solubility. And the solubility of a particular solute is the maximum amount of that solute that will dissolve in a given quantity of solvent at a specific temperature. So for example, you might be given a solubility of 40 grams of a particular solute per 100 milliliters of H2O, or water, at 60 degrees Celsius. So what this means is that in 100 milliliters of the solvent, we can dissolve 40 grams at that temperature. Now it's important to identify the temperature because the solubility is dependent on temperature, as we'll see when we look at solubility curves. But also you can understand this conceptually because the higher the temperature, the more easily the solute particles will be able to be separated from one another, making it easier for the water to hydrate those solute particles. Now, when we discuss solubility, we can identify different types of solutions. We can identify an unsaturated solution, a saturated solution, and a supersaturated solution. And the difference between these solutions is the relative amounts of solute that are dissolved compared to the solubility of the substance. When you have an unsaturated solution, you have a solution where you're holding less than the maximum amount of solute particles. When you have a saturated solution, you're holding the absolute maximum amount of solute dissolved in this given amount of solvent at the temperature that you're at. A saturated solution is quite stable, and that's important to note. This is the most stable form of the solution. A supersaturated solution is one where more than the maximum amount of solute is dissolved in the given quantity of solvent at the temperature specified. A supersaturated solution is difficult to form and it's very unstable, as you saw in your Introduction to Solutions experiment. Now, without having values like the solubility or the curve that you'll see later on, we can use what's called the seed crystal test to identify the type of solution we are presented with. This test is performed by adding one crystal of the unknown solute to the solution. What we observe will help us to decide what type of solution we had. So if the crystal we add dissolves, then we know that the solution was unsaturated. It was holding less than the maximum, so when we added the one extra crystal, it simply dissolved because there was space for it. If the crystal simply settles to the bottom, then we know that the solution was saturated. The solution is not disturbed because, as I said previously, it's quite stable, but because the solution is holding its maximum amount of solute, it will not accept or dissolve any more solute. A final scenario is if the addition of the crystal causes crystallization. And crystallization is observed when you see crystals growing in the solution, and it appears as though the solution may be freezing, even though it's not, or the crystals are essentially falling out of solution. If that occurs, then we know that the solution was supersaturated. This highly unstable solution couldn't hold any more crystals, and so therefore, by disturbing it with the addition of one extra crystal, all of the extra crystals fall out of the solution. Now what's important to note here is that the solution is returning to a saturated state. So all of the extra crystals will fall out of solution. Now, solubility curves are a useful way to study solutions quantitatively. We can identify a type of solution, or we can identify the amount of a particular solute that can be dissolved in a given amount of solvent. And what's important to note is that any point on these curves is a saturation point. So what that means is, if I look at this point, for example, the curve that I'm studying is potassium nitrate. And what I see here on the y-axis is I see 150 grams. And this is 150 grams of solute, so 150 grams of, in this case, the potassium nitrate, per 100 grams of water. The density of water is 1 gram per milliliter. So when we're referring to 100 grams of water, that can essentially be viewed as 100 milliliters of water as well. And the temperature that this is occurring at is, in this case, I'll estimate it to be about 78 degrees. So this point on this curve is showing me the solubility at 78 degrees Celsius. 150 grams of potassium nitrate can dissolve in 100 grams of water at 78 degrees Celsius. So this is an example of a saturated solution. This is the maximum at this temperature and with this amount of solvent that I am able to dissolve. If we consider a point above the line, so say we have a scenario where we have 160 grams dissolved in this 100 grams of water at this particular temperature, then what we have is a supersaturated solution. Because if I have a solution that has 160 grams, that is more than the maximum, where my maximum is 150 grams. At the same time, if I'm below the curve, so if I have a scenario where I have 140 grams dissolved of potassium nitrate at this temperature, then I have an unsaturated solution, because that quantity, 140 grams, is less than the maximum amount of solute. Now what we're going to do is look at some problems that we can do using the solubility curve. So in the first one, it asks us to state the solubilities of each of potassium nitrate and sodium chloride at 20 degrees Celsius. So what we want to do in this case is we want to identify the solubility. We're looking for a point on the line at that particular temperature. So the black line here is the potassium nitrate. So I'm going to go up from 20 degrees, and there's my point on the line. And for the sodium chloride, I've got the yellow line that's just a little bit higher. And what I want to do is read the Y value at that point. Now, as you can see, the scale isn't ideal, so we're going to have to be a little bit lenient in terms of how close we are to each other in the values that we choose. Maybe just do the best that you can to read off of the scale. So what I estimated for the potassium nitrate was that 30 grams could dissolve. And for the sodium chloride, I estimated that 35 grams could dissolve. So therefore, to write the solubilities, when we want to write the complete solubility properly, we need to state the amount of solute, so 30 grams of potassium nitrate in 100 grams of water at 20 degrees Celsius. Okay, that's the full appropriate solubility. For the sodium chloride, we have 35 grams of sodium chloride per 100 grams of water at 20 degrees Celsius. The next question states, generally speaking, what effect does an increase in temperature have on the solubility of an ionic compound? How? So when we look at, in general, except for sodium sulfate and cesium sulfate, which in these cases, these substances, as temperature rises, there is some decomposition that occurs, which results in a lowering of their solubility. But in general, we have an increase in solubility as the temperature increases. And the reason for that is that dissolving is a process where we need to first break apart the solubility, the solute particles. So increasing the temperature generally increases the solubility because there's more energy available for breaking apart the solute particles. Okay, so more energy, and you can continue to break up the solute particles. Which, if you think about in terms of an ionic compound, when you've got your positive and negative ions that we're trying to break apart, that's going to require some energy because they're tightly bound. So when there's more energy available, it's going to promote that process and therefore increase the amount of solute particles that are able to be dissolved. Next question, would a solution containing 50 grams of potassium nitrate in 100 grams of water be unsaturated, saturated, or supersaturated at 40 degrees Celsius? So when we're given a point like this, what we want to do is figure out where we are relative to the line. So we're given that we've got 50 grams of potassium nitrate, and we're at 40 degrees Celsius. So we want to find that point, which is about here. And then we want to look at where we are relative to the potassium nitrate curve. Keeping in mind that on the curve, that's an example of a saturated solution. So if we're below the curve, this is an example of an unsaturated solution. So when we have 50 grams of potassium nitrate dissolved, it's going to be unsaturated. And an appropriate explanation would be that this is an example of a point below the curve, or you could state the point on the curve at 40 degrees Celsius and then show that 50 grams is less than the saturation point. At what temperature would a solution containing 50 grams of potassium chloride in 100 grams of water be saturated? So this time, we are given the amount of the potassium chloride being 50 grams, and we want to know at what temperature that's going to be saturated. So what we want to do is go all the way across and find the point at which we intersect with the graph, and that point happens at about 80 degrees Celsius. So we're right about here. So at 80 degrees Celsius, this solution will be saturated. Again, saturated is any point on the line. The next question, what type of solution will a solution containing 120 grams of potassium nitrate in 200 milliliters of water be at 30 degrees Celsius? Now, in this case, you want to be careful because what you're seeing here is not the volume of 100 milliliters as we see on the graph. So what we need to do is we need to set up a proportion so we can figure out what the equivalent of this is in 100 milliliters. Okay, and this one is relatively simple because we are halving the volume. So some of you might see right away that the amount of potassium nitrate is going to be halved as well. So we're dealing with a scenario where we have 60 grams in 100 milliliters of water. This is basically an equivalent solution. If you don't see that right away, then you can simply cross-multiply and solve for x, and you'll end up with 60 grams. So what we're looking for is what type of solution we have if we've got 60 grams of the potassium nitrate dissolved in the water. So again, I'm trying to find the point on the line. And I'm at 30 degrees Celsius, so my point is right about here, which is above the potassium nitrate curve. So therefore, this type of solution is going to be supersaturated. So it's important to note what it means when they say what type of solution do you have. They're asking if the solution is saturated, unsaturated, or supersaturated. In this last example, we want to know what amount of sodium nitrate in grams will be crystallized if a saturated solution containing 100 grams of water cools from 70 degrees to 5 degrees. So we've got sodium nitrate, and we're cooling from 70 degrees to 5 degrees. Now, for the most part, it's really difficult to make a supersaturated solution. So for the most part, if a saturated solution is cooled, it's going to stay saturated as it's cooled down, and any excess crystals will simply fall out of solution, and you'll see them crystallized. So what you need to do is read off the graph, and you can take a moment and find your values. I've estimated at 78 degrees Celsius that we intersect on the sodium nitrate curve at 138 grams. So this means that in 100 grams of water at 70 degrees Celsius, we're able to have 138 grams of sodium nitrate dissolved. While at 5 degrees Celsius, the same 100 grams of water can only hold 80 grams of solute. Therefore, as we cool from 70 to 5, the amount that falls out is going to be the difference between the two. So 138 minus 80, which is going to be 58 grams. Okay, and that concludes our lesson on the basics of solutions and solubility curves.